Hello again. Right, welcome to part two. This is on polysaccharides. If you missed the first one on mono and disaccharides, please make sure you watch that first because it's going to go into detail about how the glycosidic bonds are formed. Okay, so the polysaccharides we need to be aware of are amylose, amylopectin, glycogen, and cellulose. So first thing, they're all different, but they've all got lots in common. So the first thing they have in common is they are all a chain of glucose molecules all joined together, but they've all got slightly different properties and therefore they've got slightly different roles, or that some of them are better at doing a role than others. So a quick reminder, when we do our glucose bonding, I'm sure when you're using your piece of paper you'll be much neater than me. So hopefully you can guess here that I'm drawing an alpha glucose, because the H is above there on the right hand side, and that alpha glucose can bond with another one, when these hydroxyl groups interact with each other. Let's get rid of that O as well. And then we're going to get our oxygen bridge. And this is going to carry on and on. There's another one, and so on. Okay, so you can practice drawing. You're going to do it much neater than me as well. There you go. So I'm starting to form a chain of alpha glucose, and this could go on for hundreds and hundreds. So if you're putting together a chain of alpha glucose, well, that could be amylose. Amylose is alpha. It could be amylopectin, or it could be glycogen. So that's one thing these three have all got in common, but how they're grouped together is slightly different. So one thing, again, they've all got in common is because of the way they're bonding here, they're all 1,4 glycosidic bonds are taking place with them all. But then amylopectin and glycogen are slightly different. So just to give you a little bit more insight into amylose and amylopectin, you've probably heard the more common term of starch. So starch is what plants produce as a way to store energy. So potato plants, they store their starch in the potatoes, or rice. So that's all that glucose that plants have been producing in photosynthesis. They need to store that for the winter, so they've got some energy storage when there's less sunlight. But the way they store it is slightly different. So amylose is only what we call 1,4 glycosidic. So it's just one big long chain like this. And that chain, as it keeps doing that, the hydrogens and the hydroxyls, they're all sort of interact with each other, forming hydrogen bonds. And what that does is the amylose shape, I'll just write amylose, so it starts to form a helical shape. It's this big, long, spring-like coiled chain of alpha glucose. And that's useful because it means that in terms of storage, it's very compact. So that's good. If you can squeeze more energy into a smaller space, that's going to be useful. Okay, so amylopectin has all this going on as well, but it has another thing going on called the 1,6 glycosidic bonds. So let's have a look at that now. I'll just quickly rub this out. So now we're talking about amylopectin. So 1, 2, 3, 4, 5, and 6. 6 at the top. There's our 6. There's our 6. I'll just do the 4s, the ones. Sorry, yep. 4, 1. So, yep, you get the 1,4, but in amylopectin, you can also get glucose molecules branching off here as well. I'm drawing it badly now. So you're getting glucose bonding, just exact same formation. You're still getting the condensation reaction happening, but now they're branching off carbon-6. So if we do a simple version, we've got, there's our chain of alpha glucose forming 1,4 glycosidic bonds. And if we call these monosaccharides, these glucoses, units, every 25 subunits that's there, every 25 subunits or every 25 glucose molecules, it's going to branch off from carbon number 6. So amylopectin has got branches. So that's really useful because the way that plants or animals can access glucose, they can only access the glucose molecules which are at the ends. So if we imagine, let's do another one. I know I've not done over 25, but just for I haven't got enough space to draw them all. If this was just a chain like amylose, that the plant could only access this glucose at the end and this glucose. There's only two ends, but once you start incorporating branches, there's now another end. So just these two branches alone mean that the plant can access double the amount of glucose that it would if it was just amylose. So it's even better for storage. It means that it's still going to be coiled up like so with weak hydrogen bonds holding those coils together, but there's also going to be branches coming off as well, those coils. So it's a more complex molecule. Okay, let's move on to glycogen. Glycogen's the same as amylopectin. The only difference now is there's more branches, and that's important for animals because let's just wrap this out as well. We're very energy hungry organisms. We require a lot more energy than a plant does. So if we're to, after you've eaten food and you don't eat for a few hours, your blood sugar levels are going to drop down pretty quickly. So there needs to be a way for you to break down the glycogen in your liver to be able to maintain your energy demands. So again, glycogen has got these 1,6 bonds as well, but now there you go, there's our 1,4, just like amylose and just like amylopectin, but glycogen has got even more branches. Again, I'm exaggerating the distances just for the picture, but you can see now glycogen's got loads. So rather than just remember the glucose can only be accessed at the ends. The enzymes can break the end ones. We've got one here, got another one, another one, another one. So the rate at which we can break down and access glucose is even better when it's glycogen. And that's good because animals, we have a much greater energy demand. We move, we have to maintain our body temperatures. All these things require a lot of energy. So amylose, amylopectin, they are considered starch, just two different types of starch. One with only 1,4 glycosidic chain, and the other one's got the chain plus the branches coming off it. They're both for storage, both found in plants. Glycogen, very similar to amylopectin. They're both insoluble. It just has more branches because we are animals and we need to be able to access more glucose at the same time. So 1,4 and 1,6. So the last one now is cellulose. This is plants, and this is what's found in the cell walls. So it's a completely different structure now. It's something that's been made from beta glucose. So we're going to talk about how the beta glucose molecules are joining together and what impact that has on its shape and structure. So I'll just rub this out. So if you remember, beta glucose differs from alpha. Not there though. All that's the same. All this on the left hand side is the same. The only thing that differs is the hydrogen here is now below. So when we put two beta glucose together, so I'll draw another one now. You'll see that the two hydroxyl groups, they're not lining up. They're too far away from each other, and therefore they're not going to be able to react with each other. So let's put our OH there. So the minute this and this, they can't react with each other. So they need to be able to align themselves. So how that's going to happen is this molecule here, you'll see how I changed the picture around now. It's going to flip upside down by 180 degrees. So if we did that, you would see that this bit here now faces this way. This hydrogen and this OH, they're going to swapped around as well. So let's swap that around as well. So now the OH is up here, the H has gone down, and now we need to swap this oxygen around as well because that's in the wrong place. And finally, that will have changed as well. So there we go. So now this beta glucose is completely upside down. So good to practice drawing that as well. So because that can happen now, these two hydroxyl groups can interact. Same thing, condensation reaction forms. And now you're going to get a structure which looks something that's, I'll do an even simpler image. You'll see how the oxygen, in fact, I've drawn it here, over here. You can see how the oxygen bridge is down below and then it's above. And it goes below, above, below, above, below, above. So it keeps swapping from being up and down because every second glucose molecule is being flipped upside down. So when this happens, rather than it coiling up, the chain of glucose stays in a perfectly straight line. There's no coiling happening whatsoever. And that's useful now because it gives it a really consistent shape. And that's useful for things like the cell wall. So if we look over here now, just change the colour actually. What I've drawn here is very small. Let's see if I can just zoom in a bit actually, see if it lets me. No, it's not. You can see I've got my beta glucoses have interacted to form 1,4-glycosidic bonds, one after the other, big long chain. And rather than it coiling, they are staying in nice straight lines. So this is it really zoomed in. This part is showing it really zoomed in. If we were to zoom out, it would just appear to be big long strings, very thin strings. And these big long thin strings, we call these chains of cellulose molecules. And these, if you've ever seen a rope, how a rope is made, it's loads of really tiny fibers put together. And this is really similar to how cellulose forms. Every single one of these chains, you can see these dots, if you remember from hydrogen bonds, they are hydrogen bonds. They are interactions, which means the chains are sticking together. So one chain by itself isn't that strong, but many of them bonded together are starting to make something stronger. And we call that collection of these chains a microfibril. So you can see how they've all gone in to this part here. And microfibrils, they're all bunched together to make something bigger called a macrofibril. And the macrofibrils are also bunched together to make the complete structure, which is the cellulose fibre. And this is what's found in the cell wall of plants. It's really, really strong as a collective of all these chains put together. So for us, cellulose is not for plants as well. It's not an energy store, and it's not something we can use for energy either. It's good for us in our diet because it's what we call fiber, so it helps to keep our digestive tract clear, because we don't have the enzyme to break these bonds here, so it passes straight through us. We can't break it down then for the glucose to get into our bloodstream. So for a plant, cellulose, its job is not storage, it's support. Notice so all the other three, they're all energy storage. This one is just support, and it's only got the 1,4-glycosidic. So yeah, quite a lot to remember there. You need to practice drawing 2 beta glucose molecules forming a disaccharides. Okay, so that's something, it takes a bit of time. So this is not a very neat one. Let me just get rid of the water so we can see it with the actual, just with the oxygen bond, the oxygen bridge. So it should look something like that. And you know you've drawn it right because on the left-hand one, carbon 6 is up here. And on the second one, the carbon 6 should be going down. And if you want to draw another one, the carbon 6 should be pointing back up again and then pointing back down. So it's that gives you an idea of if you've drawn it the right way around. All right.